Hey folks, Doug Blake with Body Design University. Welcome to our weekly study. And today we're going to talk about the force velocity curve. This is in response to somebody I just actually asked a question because they had seen a or they had gone on a quiz. I think it's Stephanie Mills had asked a question inside the group. Just keep in mind, anytime you do something like that, you ask a really good question, you want something explained, I'll just go ahead and do a study specifically on that topic. So this one for Stephanie asked a great question, which is, I'm doing the NASM materials, I get to a quiz question and I don't get it. And I'm sure that Stephanie probably went through the chapter, looks through the material, and like most folks, believe it or not, particularly in chapter 7, and this is the 7th edition, the questions related to issues like kinesiology, biomechanics, these really sort of geeky, hardcore type of scientific questions, which for the most part have little to no relevance to the personal trainer in the real world, right? It's just the reality of it. Now, if you're in sports conditioning or if you're in sports or athletic type of scenarios with athletes, even such as power lifters and other strength and power related athletes, yeah, this stuff is pretty important. I mean, heck, that's what I studied. It's really cool, but again, it's kind of geeky stuff in one sense. It's one of the reasons why when we talk about how to particularly study for the NASM test, that's why we kind of talk about this certain areas where a lot of it is just rote memorization. You just got to memorize concentric, force, velocity, inverse relationship, yada, yada. And by the way, that's why NASM themselves, if you look, and I'm just looking at chapter 7, and this particular, by the way, this is all a warm up, Stephanie. So just hang in there. It's one of the reasons why NASM themselves give the force velocity curve information 3 paragraphs and a chart, and a very simplified chart. Thank you, NASM, because when I studied this stuff back in college, it was a ton of material, and there was a lot of information, lots of graphs, and lots of really cool stuff that had little to no relevance in the world of personal training with the average, apparently healthy client. But the information is helpful in some sense, just like knowing some of the more, arcane muscular anatomical information that we see in any of the top certifications. Nothing wrong with it. You got to pass their test. So that's why I want to go over this with you sort of as an introduction to help you get a little better grasp on not just, look, the memorization of it is really simple. There's basically 4 options. So let me start with that. Before I even show you the PowerPoint, the memorization is really if you wanted to, just for the sake of answering correctly the question on the exam, it's very simple. You have eccentric and concentric contractions, and you have the forces that they are able to produce within those type of contractions, right? Concentric shortening, eccentric lengthening, depending on the total amount of force that is being generated. The actual speed or the length at which the muscle can lengthen eccentrically or shorten concentrically is A, B, C, or D. If it's an eccentric contraction, your memorization, what you're writing, rewriting, saying out loud over and over again until it's just stuck in your head, is that eccentric force development, right? As force increases, the velocity increases. Okay, so increase in force, increase in velocity. That's eccentric. So that's simple enough. Force and velocity increase. So if you see a question related to the force velocity curve, if the force increases, the velocity increases. If the velocity is able to increase, okay, the force is increasing. If the velocity decreases, the force decreases. That's the eccentric. That's just pure memorization. With concentric, it's inversely related. It's an inverse relationship. Force increases, velocity decreases. Done. Write it down over and over and over and over, and you'll get the question right. Whether you understand it is a completely different question. Okay. And so that's why doing a weekly study, or at least kind of going into a little more, should help you. As a trainer, it's not a bad idea to kind of know these things. Why? Because you may actually come up against a scenario where it would be helpful for a strength athlete or a track and field athlete, somebody that's going to need to understand a little bit more from a training perspective, or how you're going to train them when it comes to your programming. In other words, if I'm training and I've trained a number of, relatively high level track and field. So I had a javelin thrower, right? NCCA javelin thrower. Really, dude was really, really good. The javelin only weighs what it weighs. It doesn't get heavier. It doesn't get lighter. So in order to throw it further, he has to generate more power. And this is where the personal trainer that understands the force velocity curve, even length tension relationship, and some of those other more arcane concepts in the biomechanic kinesiological field, that's where that can come in handy, right? Because ideally we want to increase power, which is work over time, right? You can see a lot of these things come together. So that's where it could be helpful. But if you're never training anybody like that, and you're doing small group training or one-on-one, and you just helping people lose body fat, just answer the question. And remember, eccentric, force, velocity, right? They're related directly. For concentric contractions, when the muscle is shortening, it's just the reverse. Increase force, decrease velocity, meaning how fast or relatively fast the muscle can literally shorten under a particular load or force generation capability. Okay, so with that said, I hope, by the way, that might actually answer your question right off the bat, Stephanie. So I'm just kind of letting you know that that's my introduction, and it's not going to take very long for me to kind of flesh this out for you. And I'm just going to draw a couple of things. But for the force velocity curve, it's just a brief review. Once again, personally, I love this stuff because it gets you into the geeky kind of academic and into the sports related realm. Like I say, this stuff is really actually important when it comes to issues related to generally sports type of scenarios and power, speed training. Again, it's not that you would never see it or have to use it. It's just, in general, it's not really information that's used in the real world. But we're not interested in that when it comes to passing the NASM test. And that's what we want you to do. So we want you to get it right, even if you're not fully understanding. But here it is. It's really, in one sense, it's very simple. And I like the way NASM, by the way, you'll see this. You'll see, well, that's a length tension relationship, but you'll see other FV curves that have the eccentric on one side and the concentric curve on the other. It's a little confusing. And I'll be honest with you, a lot of the reasons why students that are going through this particular area, this part of the material, can get confused is simply because those of us that are in the academic part of this, we sort of assume certain things. We assume you already know certain things about the sarcomere, that you already understand the force tension relationship. You already understand actin and myosin overlap in a sliding filament theory. Those are sort of assumptions that are made so that when we come to the force velocity curve and we start talking about the ability of a concentric contraction speed, or the reason concentric contraction speeds is not as consistently high as it can be as force increases, is because generally it's going to be because of the overlap of the actin and myosin filaments. And as the actin, you see, if you don't understand just the basics of a sarcomere, which is where you have actin filaments and a central myosin protein component with actin myofilaments on either side moving towards each other towards the Z line, okay, there's going to be a problem, or the Z line's moving closer into the A band. So if you don't understand that, that's where this can get confusing. If you go back and look at it, it'll make more sense. As a sarcomere shortens, right, through a concentric contraction, right, it's those actins on either end of the central main myosin molecules within the sarcomere, they start to sort of bump into each other. Okay, the total number of cross bridges decreases from the ideal length of the muscle as it shortens. So therefore, as it shortens, it simply doesn't have the same capability, for instance, to create cross bridges, and then they start bumping into each other when they come to the central part of the myosin molecules themselves. And with that, all of a sudden, we're back to the force velocity curve. And that's one of the reasons why, as muscles shorten and you try to increase the speed of shortening, you're going to have to use, quote, less resistance. This is where it can get a little confusing. Think about a dumbbell curl. So if I got a dumbbell curl, right? Just think about a dumbbell curl. I'm taking a 5-pound dumbbell curl. How fast can I curl a 5-pound dumbbell curl? Okay, it's 5 pounds and there's force generation in my muscle. Now compare a 5-pound dumbbell curl and how fast I can curl it compared to a 50-pound dumbbell curl. What is the speed at which I can curl a 50-pound dumbbell curl versus a 5-pound dumbbell curl? Obviously, I can't curl 50 as fast as I can curl a 5. I can take a 5 and pull it up really quick, which means that the muscle, the bicep muscle itself, the sarcomeres inside, are shortening quicker. Okay, so their velocity, or the velocity of shortening, is significantly faster than the available, or the ability of those same sarcomeres to shorten speed-wise as when I'm holding a much higher load, or much heavier load. That relates to the force development. So my bicep, when it is pulling a 5-pound dumbbell, is not generating a lot of force. Okay, it's one of the reasons why I can pull the 5-pound dumbbell that fast. But what force development do I have to achieve in order to curl a 50-pound dumbbell? It's significantly higher, not just by the number of muscle cells that are, or motor units that are being activated, but the actual internal components of the sarcomere itself. So these are the reasons, or these are the considerations that we are thinking about when we look at just the force velocity curve. And by the way, that's the blue guy, right? So let me go ahead and put let me put a little pen on here. That's this guy right here. The blue one is the concentric curve, right? So it's going to be high velocity, right? High velocity, low force, or you can say muscular force, high force, right? Very low, zero velocity in one sense. And then as the force decreases, well, you're able to actually increase the velocity of the contraction. Okay, so your x-axis is speed, or technically you can say how fast the muscle can shorten, i.e. how fast the sarcomeres can shorten, versus how much force is being generated. Okay, so that's the concentric on the blue. Okay, during an eccentric, and by the way, do you know the difference between concentric and eccentric? Yeah, you would have read through it, because eccentric now is when the muscle is lengthening. Technically, eccentric contractions are understood to be tension development to resist or slow down the lengthening of a particular muscle under a load, right? So concentric is the actual shortening of the muscle to actually move a load from point A to point B. Then technically the eccentric is understood to be the contraction that takes it back to its original position, but under controlled, slow contractile speed, right? So if I let down the dumbbell, I'm controlling its descent, is one way to look at it. But here's the thing about the eccentric versus the concentric contraction. You have added elements that will assist with force development, right? You ever notice you can let down a heavier dumbbell? That's why we have eccentric training. You can let down or eccentrically contract, right? Eccentrically contract, muscle lengthens under tension with significantly heavier weight, 25, 30% heavier weight to control and lower it than you could ever lift. You can't curl a 40-pound dumbbell, but you can let it down slowly. So a concentric contraction, of course, is going to have a lower force potential than eccentric anyway. So the question, of course, is why? And NASM tells you, on whatever page that was in chapter 7, that generally it's accepted that there are other non-contractile components and elements within the muscle, yes, for sure, that allow for this increased tension generation, which allows for the muscle to, again, produce force. People then say, well, why is the curve this way then? Okay. And the answer is really pretty straightforward. Is that because as I contract, now here's the thing, we're not dropping the weight. Now watch this. I can take the 40-pound dumbbell. I'm not dropping the weight. Okay. That can be a confusing part of this. A true eccentric contraction is when the muscle is tense. So now imagine this. Imagine just the real world scenario is what's probably most helpful. If I have a 40-pound dumbbell, and I start to lower it at a certain speed, there's a certain amount of tension that's generated because it's 40 pounds. Now, if I let a 50 or 60 or a 70-pound dumbbell down at the same speed, is the force going to be higher, the same, or lower? It's going to be higher because the load is heavier and I need more muscular activity to simply lower the weight down. Here's the kicker, is that as I lower the weight down at a faster speed, think about this, I'm not dropping it because that would be zero contraction, but as I allow the weight to go down faster, right? 40-pound, 50, 60-pound dumbbell, I let it go down faster, the actual total amount of force generated or able to be generated actually goes up as long as tension is developed. And this is what now leads. So there's your memorization. That's the memorization part of it, right? Concentric, eccentric, increased force, increased velocity, eccentric, increased force, decreased velocity. The point is that this is now what NASM wants you to relate to the plyometric and reactive type of training. So I hope that part is helpful because again, the memorization component of it is simple. I just told you. Understanding why, you have to now go a little deeper into the mechanical dynamics within the muscle itself. Again, because the muscle is lengthening from a shortened position, the amount of force that's able to be generated as you lengthen, as long as it's still under tension, can actually increase. Now, of course, what ends up happening is that as I increase the speed of the eccentric contraction, there's going to come a point where I'm no longer really eccentrically contracting the muscle, and now I'm just dropping it. But the point is that I can let 80 pounds down faster, right, than 60 pounds slower. Hope that makes sense. I can lay 80 pounds on a dumbbell curl, 80-pound dumbbells. They're going to pull down on me, but there will be tension developed. And the force to control that 80 pounds will actually be available versus 60 pounds where I wouldn't be able to do it. Right? I wouldn't be able to let it down really slow. Okay. So the amount of force available to be developed during the eccentric actually goes up if I let it down faster while it's contracted. And this can be somewhat confusing because I'm not just dropping the weight. That's not an eccentric contraction. An eccentric contraction is when I'm actually trying to resist the movement of the dumbbell, just as if, for instance, on the way down. So I hope that helps. Now, and all I did here was I wanted to help you understand that when you're in this chapter, part of getting through this, the FV curve, is understanding the length tension relationship. I kind of explained it in one sense. Here's the only problem. And Stephanie, you might see this again, some folks that are watching this, I looked at it and I was a little, they they could have done better with the way they drew these guys. That's my only issue with they did a great job, but there's a couple of pictures that I think could have been, done a little bit better. Generally, we don't see sarcomeres in a vertical position. I'm just saying this is by convention. Normally we see them like this, right? Actin and myosin, and this is the way we see them, right? So those are your myosins and those are your actins. They are horizontal. I don't know if it makes a difference when you're going through it, but it can be a little confusing. I think that's just my personal opinion. I would have done a horizontal picture. Now, again, even just the length tension relationship curve can be a little confusing. I don't want to go over that with you on this particular study. We can, if you want, I can do another study on it. The point is that the length tension relationship correlates with the force velocity curve because of the mechanical nature of the sarcomere. And you can see that the length tension relationship basically tells you where the maximum tension development, right, or potential for maximum tension is developed based on actin and myosin overlap. Well, obviously, as the muscle is lengthening and shortening, this is where we start to see one of the problems with force generation as a muscle shortens. And obviously, there's going to be a reduction in overall force as the speed at which that shortening occurs, i.e., concentric force, right? Decreased velocity. Versus as it's going the opposite way, where now we're seeing an increase in overlap. And that's these guys right here. We see this maximum overlapping, right, of the actin and myosin filaments, so that you have the requisite or highest number of cross bridge availability. And then, of course, what's going to happen is now the force is going to, or force generation capability is going to go down. That's the only reason why I put that on there. Obviously, the entire chapter can kind of be brought together and summed up as you get to the end of it. If you have any questions, I've got to stop because I'll continue to go on and I don't want to confuse the issue if it's already doing so. Please keep in mind, let me go ahead and jump out of here and get back to what I said at the very beginning. To pass the question, to pass the test based on a question in chapter 7, you got to memorize some basic things about that curve, which is that, right, the force velocity XY axis. They tell you that in the concentric, right, high force, low velocity, and then it goes down, right? So for the concentric contraction when a muscle is shortening, it's an inverse relationship, right? The terminology, inverse relationship, increased force, decreased velocity, or you can say it the other way, right? Decreased force, increased velocity, right? So if I want to throw something faster, if I want to throw a javelin, or I want to throw the shot or discus, in order to do that faster and have a higher speed of release, right? What do I've got to do? I have to use, or my muscle is not going to be able to generate the same level of force. How that applies to training, really interesting, very cool stuff. I'm not going to get into that, of course, but the point is that that's the concentric contraction. On the eccentric side of it, it's just the opposite. Eccentric, it's a direct relationship. It's not an inverse relationship. It's a direct relationship. Increased force, increased velocity. Okay, so that's your memorization part of it. Understanding why that is a little bit more involved. But again, it's generally understood and related to non-contractile elements on the eccentric component of it. And then generally it's understood, or at least partly understood, that there's an actual mechanical disadvantage that occurs when the muscle is shortening due to not only the actin filaments kind of bumping up against each other in the central component of the myosin, over the myosin, as well as the total amount, like the length tension relationship showed us, the total amount of available cross bridges as the muscle shortens. So I hope that was helpful. Stephanie, please remember, anytime you got questions, just post them like you did, and we'll get to them and do a study on them. Yes, I think Stephanie had also asked about the Q&A every Wednesday at 2 p.m. It's available. You'll be able to see it in the group itself. You can click on that and send it to us. But keep in mind, the ability to actually explain it in a Q&A is a little bit more challenging than doing an actual study. So again, hope this was helpful. I want you all to have a great weekend. We will see you next week.